Hi guys, welcome back to your video lesson here for lesson 4.6. Lesson 4.6, we're going to kind of change gears a little bit. We've been talking about solving with using square roots, and sometimes when you go to take the square root, we can't do it very well. We've been talking for years, at least the last couple of years, in Algebra 1 as well as Geometry, we've been talking about taking the square root of numbers. And as it is, we can only take the square root of a number if that number is greater than 0, if it's positive. Well, we're going to kind of change gears on that a little bit too, and we're going to introduce a new concept called the imaginary unit. An imaginary unit is referred to as this lowercase letter I, and the imaginary unit I is defined as the square root of -1. All right? So the square root of -1, we're going to be using this arbitrary I to represent the square root of a -1. All right? A complex number is a number a plus bi, where a and b are real numbers. A is the real component of that number, where b is the complex number. And again, I'm sorry, bi is the complex or imaginary part. And so again, we call it a complex number because it has two parts. It has a real part, a, and it has an imaginary part, bi. All right? An imaginary number is any complex number in which b is not equal to 0, because if b is equal to 0, that means that this term, goes away, and you just get a real component to that number. And so that would not be an imaginary number because it doesn't have an imaginary part with it. All right, complex conjugates look very similar to what we talked about in the last lesson. If you recall from last lesson, we talked about a plus the square root of b, and its conjugate is a minus the square root of b. And the reason for that is because when we FOIL this, the middle terms are going to cancel out, and you're left with simply a minus the square root of b squared. And so we don't get that square root of b term anymore because b squared becomes b, and it's simply a minus b. All right? So we kind of talked about that in our last lesson. The same idea here is that complex conjugates are a plus bi and a minus bi. And again, the reason for that is when we FOIL this out, we get a squared, and then a times negative bi is negative abi. Bi times a is plus abi. And then on the end of this, you get positive times a negative, which is negative, b times b, which is b squared, and then also I squared. And we'll deal with the rest of this and how this cancels out. But effectively, that goes away, and then we'll deal with I here shortly when we get down to this part down here. All right? All right, the complex plane is very similar to your regular Cartesian coordinate system, but instead of having an x and y axis, we're going to have an a axis and a b axis, where a represents the real component and I represents the imaginary component. All right, we'll give an example of that towards the end of the lesson here. But again, basically instead of having an x-axis and a y-axis, you have a real axis and you have an imaginary axis. Okay. Now, I don't know why we've chosen to call this an imaginary number. There's nothing really imaginary about it. It's the square root of a -1, but we can't do that with our calculator, so we've decided to call that imaginary. All right? All right, and then finally, absolute value. If you recall when we talked about absolute value from a number line perspective, if here was 1 and here was 5, the absolute value of 5 is 5 because the distance from 0 to 5 is 5 units. All right? The absolute value of -5 is also 5 because the distance from -5 to 0 is 5 units. So when we defined absolute value, we kind of said, well, look, we take whatever's in here and make it positive, but we also talked about this idea of the distance to 0. All right? And so when we start talking about the absolute value of a complex number in the complex number plane, we want to say some arbitrary point, a plus bi, all right? And how far is it from that point to the origin? All right, and we'll get into some discussion about how we do that here shortly. But effectively, for those of you guys that remember Pythagorean theorem, okay, this is a right triangle. This real distance is a, the imaginary distance is b, and so the distance from here to here would be the hypotenuse of that right triangle. All right, and so a squared plus b squared is equal to c squared, where this is c now. Or absolute value. And then if I want to find that distance, we simply take the square root of both sides, and so c is equal to the square root of a squared plus b squared. And you see that right there? Yeah. And so instead of saying c, they say the absolute value of z, meaning the distance from 0 to that complex number, which again is effectively our hypotenuse. So we'll get some more practice with that here shortly, and I'll show you a couple different ways to do it with the formula as well as on paper. All right? Okay, so I want to go ahead and take a few minutes and look at some properties of square roots and negative numbers. First of all, it says if r is a positive real number, then negative square root of r becomes I radical r. Now, why is this true? Well, we just got done saying that the square root of negative 1 is equal to I. So if I rewrote this as the square root of negative 1 times r, because that's what the square root of negative r is, that would then become the square root of negative 1 times the square root of r. Well, we just got done saying that the square root of negative 1 is defined as some imaginary unit, I, and so instead of calling this the square root of negative 1, we're just going to call it I. So effectively what we do is we just take that negative here and we replace that with an I, and then we still have the square root of 3. All right, it's a little hard to read. Let's fix that a little bit. Sorry about that. So this becomes the square root of 3. So we pull the negative out in front because that is the square root of negative 1. We recognize that I is the square root of negative 1, and so we don't have to go through all of this process to justify it. All right, by property number 1, then, it follows that if I radical r squared, that's equal to negative r. Now, why is that true? Well, remember, from properties of exponents, way back in Algebra 1, we said that this is ab squared is the same thing as a squared times b squared. So if I have the product of two things squared, then it's basically both of them squared. Recognize, please, that this is not the sum of those two where I'm squaring like this. That's no good. When we do that, hopefully you remember that you have to FOIL. All right? But that's not what we're doing here. We're squaring a product, and so this becomes I squared times the square root of r squared. Well, I squared, let's remember what I is, guys. I is the square root of negative 1. All right, and so if I square the square root of negative 1, what's the square root of negative 1 squared? Well, squaring and square root undo each other, so that just becomes negative 1. All right? And then in addition to that, you also have the square root of r squared, and like we said before, squaring and square root undo each other, and so this is negative 1 times r, or simply negative r. Oops, negative r. And so in this case over here, you have I radical 3 squared. The I squared becomes I squared, radical 3 squared becomes 3, and as we said before, I squared is negative 1, so this is simply negative 3. All right, so where does this come into play? Let's take a look at an example where this actually comes into play. We talked about solving problems with square roots yesterday, right? And so the first thing we're going to do here is we're going to subtract 15 from both sides, and this becomes 2x squared is equal to negative 50, right? Because if I minus 15 from both sides, I get negative 35 minus 15 more, which is negative 50. Now, divide each side by 2, I get x squared is equal to negative 25. Now, back in Algebra 1, you would have said, I can't do this because I can't take the square root of a negative number. But now we've given you the tools to do so. This becomes x equals the square root of negative 25. Well, as we said before, the negative just becomes out here, and I'm left with the square root of 25. All right? Now, we can go ahead and take the square root of 25. This is simply 5. And so we write the real component first. All right? So the 5, the square root of 25 becomes 5, and then you have the I. All right, now one other quick note here is make sure you understand that when you take the square root of both sides, way back in this step right here, we need to consider plus or minus. Remember we talked about that last section, and so really this is plus or minus I radical 25, which becomes plus or minus 5I. Now don't think that the negative, again, that we don't have to consider plus or minus here because the negative was under the radical. We're still considering plus or minus. So my solutions are positive 5I and negative 5I. Now, these two solutions are imaginary solutions, all right? And when we get into our final lesson, we're going to talk a little bit about what that means and where those solutions are. All right, so go ahead and try the checkpoint example here, and we'll be right back with a solution for you. All right, hopefully you've taken the time to do this. We're going to subtract 13 from both sides, and I get 3x squared is equal to negative 36. Divide both sides by 3. You get x squared is equal to negative 12. And now when I take the square root of both sides, I have x equals plus or minus. And now the radical of negative 12, remember that's the same thing as negative 1 times 12, right? And so it's square root of negative 1 times the square root of 12. Well, square root of negative 1 comes out in front and becomes I. Now, can I split 12 up at all? Well, remember our little chart from our previous lesson. You have n and n squared. Again, 1, 2, 3, 4, etc., etc. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, etc., etc., right? So we said familiarize yourself with that chart. Are there any of these perfect squares that evenly divide into 12? Well, 12 is the same thing as 3 times 4, isn't it? So I can't take the square root of 3. It's not rational, so we're going to leave that as radical 3, but what is the square root of 4? Well, it's 2. So the square root of negative 12 really is the same thing as the square root of negative 1 times 3 times 4. And you might ask, well, why did I split it up that way? Well, the square root of negative 1 becomes I. The square root of 3 does not simplify, but the square root of 4 is 2. All right? So we're going to bring the 2 out in front. So we're going to make this plus or minus. The square root of 4 is 2. Don't forget the I that we brought out, and you still have radical 3 left underneath the radical. So you're going to get really good at practicing, but again, you don't get good at this without practicing. But practice by simplifying radicals. The better you get at that, the easier this lesson is going to be. All right. Sums and differences of complex numbers. To add or subtract two complex numbers, add or subtract their real parts and their imaginary parts. And we're going to do that separately. Okay, so basically we pull the real components together, add those together to get a plus c. Then we grab the imaginary components and add those together, and I get b plus d, I. We'll give you some examples which will make much more sense, but same thing here with your subtract. Now keep in mind with this, guys, you have a plus bi, and you're subtracting this entire thing. We've talked about subtract a number of times in this class, and how subtract, especially when you have a distribution, you're subtracting this whole thing. So sometimes it's better to say, all right, look, this is actually the exact same thing. Instead of subtracting that whole thing, is adding the opposite and the opposite. And now it becomes a plus negative c, or a minus c, and then b minus d, I. All right? So let's use that idea in our first example here. We're going to subtract the real components. Again, we're subtracting this whole thing. So I have 6 in the real component, and I'm subtracting 4. Well, 6 take away 4 is 2. Now, sometimes that's a little confusing, so what I like to do is I like to say, all right, look, this is plus the opposite and the opposite. Because subtraction says add the opposite, right? So now let's just treat it as a plus problem. This is now 6 plus negative 4 and 3 plus 1, because again, the coefficient of I here, there's only one I. All right, and so instead of doing 3 take away 1, which would have been, I'm sorry, 3 take away negative 1, we're going to do 3 plus 1. All right, and so this becomes 6 minus 4, which is 2, and then 3 plus 1 more is 4i. And so that is now 2 plus 4i. All right, what about the next one, to add? Again, now add, we don't have to worry about the sign. It's just 2 plus 7, and then the imaginary parts is 5 minus 2. So 2 and 7 makes 9, plus 5 minus 2 is 3i, so that is 9 plus 3i. Okay, so just keep in mind that if it's a subtraction problem here, just make it add the opposite of both, and I think that'll make your life a lot easier. All right, what about multiplying complex numbers? Well, multiplying complex numbers kind of takes on a little different feel to it. When you multiply, you just don't multiply the real parts and the imaginary parts. That's not how we do things. If I had a binomial, for example, x plus 2 times x minus 3, hopefully this is looking familiar to you from what we've done earlier in the chapter, we should have to FOIL that. And so because of the real and the imaginary part of that, the fact that it's a complex number, we're going to have to FOIL this out. All right, so we have to use FOIL, first outers, inners, last. Some of you guys like Punnett squares better, and we've talked a little bit about these in this class too. This is 2 plus I, this is negative 5 plus 2i, and so when I go to FOIL, this is negative 5 times 2, which is negative 10, negative 5 times I, which is negative 5i, 2i times 2, which is 4i, and then 2i times I becomes 2i squared. We'll deal with that in just a second here. Now, again, if you don't like that, just do 2 times negative 5 is negative 10. 2 times 2i is 4i, I times negative 5 is negative 5i, and then I times 2i becomes 2i squared. And you notice that we got all the same entries from our table when we use the Punnett squares than when we FOIL. Now we just have to combine like terms and do some simplifying here. Remember, I squared is negative 1. So this I squared right here is the same thing as negative 1. So what is 2 times negative 1? Well, that's negative 2. All right. Up front here, you still have negative 10. And now we have 4i take away 5i. Well, that's negative 1i. And then we simplified on the end of this thing. This is still negative 2. And so from there, then we would go ahead and simplify again. What's negative 10 take away 2 more? Because we just want to add the real components, or in this case, subtract them. But it's negative 10 take away 2 more, which is negative 12. And then we have minus I. And again, you can put minus 1i, or you can just leave it as I. And that's fine, whichever way you do it. Okay? All right, what about dividing complex numbers? Well, we don't have a really nice way to divide complex numbers. And so instead of dividing complex numbers, if I had 6 plus 4i over 2 plus I, this kind of goes back to what we were talking about, is that idea of the conjugate. Well, the conjugate of 2 plus I is 2 minus I. And so I want to multiply both top and bottom by 2 minus I. Okay, numerator and denominator. Now you might say to yourself, well, why are you doing that? What's the point? Well, we just got done saying that when I multiply, I have to FOIL, right? And so on the bottom, 2 plus I times 2 minus I, well, that's my sum and difference pattern. This is 2 times 2, which is 4, 2 times I, which is 2i, 2 times negative I, which is negative 2i, and then negative I times I is negative I squared. Now, what happens with 2i and negative I when I add them together? Those two terms cancel out, and I'm left with 4 minus I squared. Since I squared is negative 1, this is 4 minus negative 1, or 4 plus a positive 1. And so on the denominator, I'm left with one number, which is just 5. We no longer have the complex number in the denominator. And so essentially what we've done is we've rationalized the denominator, but not really done rational numbers. But it's the same process. All right? So on the bottom of this thing, as I said before, this is just going to simply be a 5. All right, on top, I'll just kind of put the 5 down here for now, and we'll just use this as our fraction line. On the top, we have to multiply 6 plus 4i times 2 minus I. And again, I kind of like the squares because for me it helps me keep things a little bit separate. So 6 plus 4i, and down the side, this is then 2 minus I. And so 2 times 6 is 12, 2 times 4i is 8i, 6 times negative I is negative 6i, negative I times positive 4i is negative 4i squared. All right, now when I combine like terms in here, I'm going to get 12 plus 2i, and then we have to remember that I squared is the same thing as negative 1. So negative 4 times negative 1 becomes simply positive 4. All right, now on the top, just go ahead and combine like terms, and we can just kind of skip this step in here. And so this is 4 and 12, which makes 16 plus 2i all over 5. All right, so 4 checkpoint problems. Basically, you got like one of each. You got to subtract, you got to add, you got to multiply. You know, a few things in here. So go ahead and give these a shot and see how this goes for you. We'll be right back with solutions for you. All right, recall that when you're subtracting, you are simply subtracting. So this is going to be the same thing as add the opposites of positive 16 and positive 3i. So instead of subtracting those two, we're going to go ahead and we're going to add the opposites. So 12 plus a negative 16 is negative 4. Negative 2i minus 3 more I becomes negative 5i. All right, I'm going to jump right to this last one here because this is simply add. Add the real components. 4 and negative 6 is negative 2. Now add the complex components. This is 4 plus 3, which is 7i. All right. Okay, so let's jump. I'm kind of jumping around a little bit here, and that's okay. Look at number 3. This is multiply. You're just distributing, guys. It's just negative 36i, because 4 times 9 is 36. You still have the I. Now this is an I squared, so we don't have to worry about simplifying it all. In the second term, this is negative 4i times positive 5i. So that's negative 4 times 5, which is negative 20, and then I times I gives me I squared. Now, hopefully you're recognizing the fact that this is I squared. This does need to be simplified. I squared is the same as negative 1. So I'm going to change the subtract to plus the opposite now. So now I have negative 20, and then I squared is negative 1. So what's negative 20 times negative 1? Well, if you guessed that that's positive 20, you're in good shape. Now, don't forget about the I here. That's still with your 36. All right, now just a real quick kind of technical thing. Remember, we always put the real component first, so we're going to change this to 20, take away 36i, all right, because we always want the real component first. The most challenging example here is that idea of getting rid of the imaginary component in the bottom. So what do we multiply 3 plus I by to get rid of it? Well, we have to multiply it by 3 minus I, and knowing that those middle two terms are going to cancel out. So this is 3 minus I and 3 minus I. We're multiplying both top and bottom by 3 minus I. Now listen, I'm not going to take the time to FOIL this bottom product out because we already know that when it's sum and difference, it becomes the first thing squared, which is 9, minus the second thing squared, which is I times I, or I squared. All right. So on the denominator, you're going to have 9 minus I squared. Let's go ahead and finish simplifying the denominator. This is going to be I squared, which is -1. And so it's 9 take away -1. Well, 9 take away -1 is the same thing as 9 plus 1, which is 10. So the denominator of my fraction is simply 10. On the top, though, we do need to do a little bit of work with this. And like I said, you can FOIL if you want. Punnett squares work better for me just because I like to keep things a little bit more organized. Kind of helps me to do that. So this is 3 minus I and 8 plus 4i, and then we just multiply. 3 times 8 gives me 24. 3 times -4i is -12i. 8 times -I is -8i, and then -I times -4i becomes plus 4i squared. All right, go ahead and combine like terms. This is -8i and -12i, so altogether these make -20i. And again, this is not I squared, so we don't have to worry about changing the sign. This I squared right here, I know is going to turn into a -1. So this becomes 4 times -1, which then tells me that this bottom box is simply -4. All right? Okay, so now I have 24 minus 20i minus 4. I now just add the real components, or in this case subtract. 20 take away 4 becomes 20, and so this is 20 minus 20i. All right, you might think, hey, I'm done. Cool. Well, sorry guys, not quite. Because both of these are divisible by 10, you can write this as 20 over 10 minus 20i over 10, and then we can simplify. 20 divided by 10 is simply 2, and again, 20 divided by 10 is 2, and so this actually simplifies all the way down to 2 minus 2i. That last step is not always the case. In fact, we didn't get an example like that before, but realize if the top two numbers in the numerator are both divisible by the denominator, we got to simplify our fractions. All right, so that's just a cool little additional step for that one that may or may not have been confusing. Hopefully that went well for you, but certainly we can ask questions as needed in the next class period. So plot complex numbers and complex number plane. Now we're going to get into that idea that this is my real axis, this is my imaginary axis, and so if I want to plot 4 plus 3i, I go over 1, 2, 3, 4, plus 1, 2, 3, and so 4 plus 3i is 4 plus 3i. That's that imaginary number over 4 up 3. What about -5? All right, and so again, I don't really worry about filling all this stuff out for right now. For letter B here, all right, that says go left 5 on the real axis, 1, 2, 3, 4, 5, and then down 4 on the imaginary axis, 1, 2, 3, 4. And so that's -5 minus 4i. Pretty straightforward business, right? All right, so absolute value of a complex number, we just got done saying in the previous example, this is the same thing as absolute value is the non-negative, right? Because we know distance can't be negative. So it's non-negative real number defined as the absolute value of z equals the square root of a squared plus b squared. This is the distance from z to the origin. Now, you don't actually have to draw this, all right? You don't actually have to draw this for the next couple examples once you memorize the formula, which really the formula is kind of a result of something that we already are familiar with, which we'll get to in just a second. If you can remember that the absolute value of that complex number is a squared plus b squared, you'll be in good shape. But for some of you that need that justification, for letter A here, that's positive 6, 1, 2, 3, 4, 5, 6 on the real axis, and then -8 on the imaginary. And so this is over 6 and this is down 8. Now, it doesn't matter that we went over 6 and down 8. If I were to draw this here and I want to know what is that distance, that's my absolute value, that's my z. Okay? I can make a right triangle out of this and say, all right, well fine, the distance from the origin to z is the distance along that diagonal right there And if I make that into a right triangle, I know that this distance right here is 6, and I know this is down 8. Well, that means the length of that leg of the triangle is 8. All right? So to find the hypotenuse then, that becomes 6 squared plus 8 squared equals z squared. And if I want to find what z is, I simply take the square root. And so that's where this comes from. It's just a squared plus b squared. Now you might think, well, what if b is negative? Well, remember, if b is negative like this here, well, when I square it, it becomes positive anyway, so who really cares, right? So this becomes 6 squared plus negative 8 squared. Well, 6 squared is 36, and negative 8 squared is 64. And so 36 and 64 is 100. The square root of 100 is 10. And so the distance from 0 to that point right there is 10 units. If this is 6 and this is 8, this is 10. All right. How about how far is it from 0 to negative 6i? Well, let's think about this one. All right. Think about that in a complex number. This says the real component is 0, right? Because this is 0 minus 6i, right? And the imaginary component is just down 1, 2, 3, 4, 5, 6. Okay? So that says it's just down 6 units. Well, how far is it from there to there? It's 6 units. So if you recognize that, okay, it's 6 units. If you didn't, then you can say, all right, well, the real component in this case is 0. The imaginary component is negative 6. So what's 0 squared plus negative 6 squared? Well, 0 squared is 0. Negative 6 squared is 36. And then the square root of 36 is 6. So you can do it visually, or you can do it with that complex number, absolute value formula. Either way certainly does make a difference. So try the last three checkpoint problems rather. It looks like we're plotting those distances, and then we're also going to find their distances. Plotting the complex numbers and then finding their distance to 0, finding their absolute value. All right, so your solutions for these checkpoint problems are as follows. Again, you can use the graph. You have to graph them. So this is 0 plus negative 4i. 1, 2, 3, 4. So that's just down 4. That's negative 4i. Again, there is no real component of that. We don't go right or left. We simply go down 4. So the absolute value of negative 4i, well, guys, that's 4, right? Because the distance from 4i to the origin is 4. If you didn't believe that and you're always going to trust a formula, that's fine. It's the square root of, there's no real component, so 0 squared, plus negative 4 squared. And so this becomes 0 squared and 4 squared, which is 16, and the square root of 16 is positive 4. Now, again, we don't have to worry about plus or minus here, guys, because we're talking about distance, and distance always must be positive. All right? For number 7. Okay, number 7 is a little bit different. For number 7, we have to go over 2 on the real axis and up 3. All right, and so there's the point right there, 2 plus 3i. And so how far is it from there to there? Well, again, if you want to use the picture, you can. All right, this distance here is 2 units. This is 3 units. And so we want to know what's that distance, what's the absolute value. All right? Well, we're really doing the same thing. The absolute value is equal to the square root of 2 squared plus 3 squared. Well, 2 squared is 4, 3 squared is 9, so this becomes the square root of 4 plus 9, which is 13. Now, since the square root of 13 does not have any factors that are perfect squares, this is the distance from the origin to that point is square root of 13. All right, and then finally, let's finish up on this last example here. In our last example, we have negative 3 on the real axis, so 1, 2, 3, and then plus 1, which is right there. All right, so we want to know how far is it from there to there. What's this distance z? Well, this is 1 unit, and this is 3 units. All right, and so that distance z is equal to 3 squared. Actually, technically, it's negative 3, but it doesn't really matter. Plus 1 squared, right? And so this becomes the square root of 9 plus 1, and the square root of 9 plus 1 is 10. Again, since that has no numbers in it that are perfect squares, no factors that are perfect squares, we can't go any further than that, and we're all done.